Measuring how much ice is in a glacier is challenging. Satellite pictures tell only part of the story. This animation shows how sensitive instruments, such as GPS stations on nearby bedrock, can help us determine changes in a nearby glacier. Glaciers accumulate ice at higher elevations and migrate downslope due to gravity. This animation, modeled after Helheim Glacier in East Greenland, illustrates ice draining from the Greenland ice sheet to the ocean. Large fractures, or crevasses, form where the ice flows faster than it can deform. Many glaciers end in the ocean or in large fjords. The grounding line is where a glacier transitions from being grounded on bedrock to floating on the water. Beyond the grounding line, crevasses can propagate through the glacier, causing large blocks to break off as icebergs. Zooming out, glaciers lie upon tectonic plates that maintain a buoyant equilibrium with the asthenosphere. When mass is added to or removed from the Earth's surface, the adjustment of the tectonic plates results in small changes in the elevation of Earth's surface. This process, called elastic adjustment, is an immediate response of the tectonic plate to a change in loading. The thickening and thinning of glaciers is one example of a process that adds or removes mass from the Earth's surface. These changes aren't noticeable by humans. Only sensitive instruments such as GPS can measure this subtle vertical change of the bedrock surface. Elastic adjustment, exaggerated here, occurs on short timescales and is sensitive to even small changes in mass. When the glacier is thicker, the Earth's bedrock surface lowers. When the glacier is thinner, the bedrock surface rises. The graph in the upper right will illustrate how the vertical movement of the GPS receiver changes as the glacier gains and loses mass over time. In the winter, when 2 to 4 meters of additional snow can fall on Greenland glaciers, the bedrock surface lowers due to the additional weight. Note that the surface lowers only a few millimeters for 2 to 4 meters of snowfall. In the summer, the snow that accumulated over the winter melts, and the meltwater runs off to the ocean. This loss in mass causes the bedrock surface to rise as the tectonic plate readjusts. In the summer of 2004, Helheim Glacier began to accelerate and thin, doubling the amount of ice discharged into the ocean. This increase in mass loss caused uplift of the bedrock surface that was measured by high-precision GPS. From 2004 to 2011, mass loss from Helheim and surrounding glaciers resulted in 75 millimeters of uplift. The annual sawtooth pattern shows the smaller magnitude seasonal cycles of snowfall and snowmelt. The broader 7-year trend of steady uplift of the land is caused by glacial thinning and ice mass loss. The dashed red line shows the extent of the glacier in 2001. In addition to Helheim Glacier, recent acceleration and thinning of many other glaciers around Greenland has been revealed by GPS measurements of the bedrock elevation. Bedrock uplift rates are shown here as arrows of relative vertical motion. These highlight the net loss of ice from the Greenland ice sheet that is discharging to the ocean and contributing to sea level rise. GPS monitoring has enabled us to understand glacial changes at a much more detailed level.